On the evening of August 1, 2007, rush hour in Minneapolis was underway. The I-35W bridge, a steel truss arch crossing the Mississippi River, carried 140,000 vehicles daily. At 6:05 p.m., with 111 vehicles on the bridge, it suddenly collapsed. In seconds, 456 feet of the main span plunged 108 feet into the river and onto its banks. The failure killed 13 people and injured 145. It was a shocking infrastructure failure that prompted immediate questions. How could a major interstate bridge in the middle of a U.S. city simply fall down? The answer lies not in a single cause, but in a chain of design errors, overlooked calculations, and construction decisions that had been building for decades. Bridge 9340, built in 1967, was a steel truss structure 907 feet long. It had 8 lanes carrying I-35W traffic across the Mississippi. By the early 2000s, Mediat inspections flagged significant corrosion, rusting, and warped plates. In 2001, it was classified as fracture critical. That term describes a bridge with no structural redundancy. A failure in a single critical element can bring down the entire span. Despite growing concerns, replacement plans were deferred and the focus shifted to a reinforcement project. The bridge was Minnesota's 5th busiest, a vital transportation link. By June 2007, a resurfacing and repair project was underway, which would inadvertently add loads that the bridge's hidden design flaw could not withstand. After the collapse, National Transportation Safety Board investigators zeroed in on the gusset plates, the steel plates that connect the truss members. At nodes U10 and L11, the plates were only half the required thickness. This design error dated back to the original 1960s plans. The original engineering firm had undersized these plates, and no one ever caught the mistake. According to the NTSB, the plates were inadequate to carry the design loads, let alone any extra weight. The gusset plate calculations were never independently reviewed. This was not an error of deterioration, it was a mistake in the original design that remained hidden for 40 years. The safety board concluded that the probable cause of the collapse was this design flaw, compounded by additional weight on the bridge. The NTSB found that neither Mediat nor the Federal Highway Administration had evaluated the gusset plate designs in sufficient detail during the original design or subsequent modifications. At the time, design review procedures existed for checking consultants' computations, but these procedures were not applied to gusset plates. It was not standard practice to do so. This gap meant that a critical structural component slipped through multiple layers of oversight. The report also noted that this was not an isolated event. Investigators found other instances where questionable bridge designs were certified and approved at both state and federal levels. This finding exposed a systemic weakness in the nation's bridge design review process. By August 1, 2007, a construction project was in progress to resurface the bridge's southbound lanes. According to the NTSB's Highway Construction Factors Factual Report, heavy equipment and aggregates for a concrete pour were staged on the bridge by about 2:30 p.m. They were positioned toward the south end of the center span, directly above the compromised gusset plates. The aggregates included sand, gravel, and cement, waiting for the evening's pour. This staging, while routine for construction, created a load case that had never been considered in the original design. The extra weight, estimated at hundreds of thousands of pounds, added stress that the thin plates could not handle. Combined with rush hour traffic, the total load exceeded the capacity of the under-designed connections. The NTSB determined that the U10 gusset plates were the first to fail. As they buckled, the load redistributed to other connections, which were also undersized. With no redundancy, the failure propagated rapidly. The sequence was captured by surveillance cameras and eyewitness accounts. One driver described seeing the bridge fold in on itself. The structural analysis later confirmed that once the U10 plates gave way, the truss was effectively compromised. The entire load was transferred to adjacent members, which were also overloaded. This cascading collapse took just seconds, leaving no time for escape. Within moments, the entire center span fell, pulling adjacent sections with it. Visual evidence from the docket shows the plates tearing through the steel. The design error had been waiting for a trigger, and the construction staging provided it. In the immediate aftermath, emergency responders searched for survivors. The final victim was recovered on August 20, eventually bringing the death toll to 13. The NTSB launched an extensive investigation, reconstructing the bridge from scattered debris and performing detailed computer analyses. Their final report, issued in November 2008, confirmed the design error as the probable cause. They also highlighted the inadequate review process and the role of construction loads. The collapsed bridge was replaced with the St. Anthony Falls Bridge, which opened in September 2008, an extraordinary fast-track project. The new bridge was designed with multiple redundancies and advanced monitoring systems. The incident prompted nationwide scrutiny of gusset plate designs and inspection practices. The I-35W collapse revealed a systemic blind spot. Gusset plates until then were often overlooked because they were assumed to be over-designed, but the NTSB and FHWA soon found other bridges whose gusset plates had similar vulnerabilities. For example, the FHWA's interim report on the adequacy of the U-10 and L-11 gusset plate designs detailed the calculations that should have been done. In response, the FHWA required all states to review the gusset plates of their truss bridges. The problem wasn't limited to Minnesota, it was a national issue. The collapse exposed how assumptions in design and review can persist for decades until a failure exposes them. Later, research programs were launched to improve load ratings for gusset plates, turning a tragedy into a catalyst for change. Following the NTSB recommendations, the FHWA and FHWA issued new guidelines for load rating and inspecting gusset plates. Technical advisories on non-destructive evaluation technologies were published to help detect deterioration and design flaws. The Safety Board also called for changes in design review procedures to ensure that critical components like gusset plates are independently verified. In 2010, the FHWA published a technical advisory on inspection of gusset plates using NDE, specifically addressing lessons from the collapse. States were required to inventory and rate all gusset plates on non-redundant steel truss bridges. These policy shifts aimed to close the review gap that had allowed the I-35W plates to go unchecked. The legacy of the collapse is, in part, a more rigorous approach to bridge safety. One key lesson was that redundancy matters. The I-35W bridge was fracture critical, meaning it had no alternate load paths. Modern bridge designs often incorporate multiple load paths so that a single failure does not cause tragedy. Another lesson was the importance of checking the original design assumptions, not just the condition. Inspections had focused on visible deterioration like corrosion, but the hidden undersizing was invisible to routine checks. The collapse changed how engineers think about risk in aging infrastructure. It also underscored the need for a safety by review culture. Independent verification of critical design calculations must be mandatory. The NTSB recommended that state DOTs and the FHWA place greater emphasis on the review of design calculations for critical structural components. This was a wake-up call for the entire engineering profession. The I-35W collapse occurred against a backdrop of aging U.S. infrastructure. According to the American Society of Civil Engineers report cards from that era, tens of thousands of bridges were rated structurally deficient. The Minneapolis bridge had been rated structurally deficient as well, but that rating was based on corrosion and fatigue, not the design flaw. The event highlighted the gap between what inspectors look for and the real risks lurking in complex systems. It was a wake-up call that not all deficiencies are visible. In the years following, infrastructure investment became a national conversation. The ARA stimulus in 2009 included significant funding for bridge repairs. The collapse prompted states to prioritize safety reviews over new construction, recognizing that hidden flaws could have serious consequences. The I-35W bridge collapse was not an inevitable act of God. It was the result of a design error hidden in plain sight, a review system that didn't check the right things, and a construction project that unknowingly pushed the structure over the edge. 13 lives were lost and 145 people were injured because half-inch steel plates were not thick enough. Today, the lessons from this failure are embedded in bridge engineering practices, but the reminder is sobering. Our infrastructure is only as strong as the weakest connection we fail to check. As the NTSB stated, the probable cause was an inadequate design of the gusset plates. That inadequacy was preventable. The collapse serves as a permanent reminder of the responsibility that engineers and agencies bear. When critical connections are overlooked, the consequences can be tragic. The I-35W story is one of how a single design error, compounded by decades of inattention, led to one of the most significant infrastructure failures in American history.